What is tomorrow night? Exam number 2. Tomorrow night. Where is the exam? 109 Ullman. What time is the exam?
8 o'clock.
8 o'clock at night. Okay, yes. So we'll be good to go. I guess there's another review session tonight. Guessing that's the last one. Okay, office hours still tomorrow all day. There is still time to sort out anything that's left. How many problems on the exam?
5.
What are the topics? Sinusoids.
Matrices.
All right, matrices. Yeah.
Derivatives.
Derivatives. Not integrals. Okay, so derivatives, right? Dynamics, electric circuits, right? Sketching problems, right? Graphing, sketching, dynamics, circuits kind of stuff. Beam, all right? You'll have a beam. Okay, so there it is. Same 5 classes of problems on all 3 posted exams. 5 different problems. None of the problems, obviously, will be the same. Okay. Questions? Concerns? All right, you know what to do, okay? We are moving on. We have to finish up. This week we're moving into integrals and dynamics, but we need to finish up integrals in statics. And I believe last time we were talking about centroids and centers of mass. And we had the centroid of a triangle. Okay, and I wanted to look at that centroid of the triangle, of the same triangle in a different way. Okay, and so correct, right? We did vertical rectangles last time. Is that right? And that's where we left off? Okay, so here's what I would argue. Maybe I don't want to use a vertical rectangle. Okay, maybe for whatever reason, I'd rather use a horizontal rectangle like this. Okay, where the centroid of this particular rectangle is here. Okay, and where that rectangle intersects the curve at some coordinate, x, comma, y. Okay, and so, if I want to think about calculating a centroid, for example, right, like say y bar, if you remember, it's the sum of the y bar I, ai's divided by the total areas, right? And if I look at areas that are infinitesimally small, right, then that summation becomes an integral, and that little ai there becomes a dA. Okay, and so here's the thing. If this is a horizontal rectangle, okay, then the thickness of this thing is no longer dx. I'm going to call the thickness of this guy now dy. So let me ask you this. The area, right, is the length times the width for this little rectangle. And so if the width here, or the thickness is dy, what's the length here of this rectangle? Is it the same? Is it b? So if it intersects this line at this point, and this point has coordinate values x and y, right? Then how wide is this rectangle?
X.
It's x, right? So this distance here is really x, but keep in mind, like x now is like a function of y, right? Say g of y, comma y. So this x is, depending upon the y coordinate, right, varies, right? It's for this particular value wherever it lies on the curve. So, how am I going to calculate the x value for any given y value? Yeah, right? This equation relates all the x and y values. If I want x as a function of y, I need to just solve this guy, right? Okay, so we'll do that in a minute, but clearly over here, this ai, right, is dA, and the dA is going to be x, or g of y dy, right? G of y dy, or x times dy. So I need to find x as a function of y, okay? And so I want to take this guy and solve for x. Okay, so help me out. What's x going to be? Yeah, so if we can solve this in one term, right? Isolating x, it'll be y minus h on the other side, right? And then we multiply by minus b over h, right? And so we'll cancel the h, right? And so what are we going to get? It's minus b over h times y plus b. Right? That's just solving this equation for x instead of y. Okay, great. How about this point right here? Right, the middle of this guy is, this is the x bar I, y bar I of the ith rectangle. What do you think? What's the y coordinate, y bar I? Right, that notation x bar I, y bar I means any one of these rectangles, the ith rectangle, where is its center located? So here's the rectangle. It's got dy for the thickness here. It's got x as a function of y, right? G of y for the height, the length. So the center of that rectangle would fall where? Yeah, it's half the x value, right? So this is x divided by 2. Okay, and what about the y value? If the rectangle intersects the curve at this point, which is the point x comma y, where x is a function of y, right? Then the center point of that same rectangle has what for the y coordinate? It's still just y, right? So now y bar I is just now y. So again, if I want to calculate the y bar right here, isn't this thing going to be just the sum of, you know, the y bar I, ai? The y bar I is just y, the ai is the dA, and the total area down here is just a. Okay, and finally, the point is the dA, g of y dy, this is the g of y, right? X is a function of y. Okay, and so the dA is x dy, which is g of y dy. Okay, and so I can plug that in. dA is this equation, minus b over h times y plus b, right, times dy. So now, if I want to calculate, for example, y bar, right, we can just plug it in. It's 1 over the area. By the way, what's the area of this triangle?
1/2 h times b.
Yeah, 1/2 base times the height, right? BH divided by 2. Let me make my h like my other h. Okay, 1/2 base times height. Okay, and so if that's true, 1 over the area, right, would be what? 2 divided by BH, right? So I'm going to have 1 over the area, 2 divided by BH. I've got an integral of y times dA. dA is this, right? It's minus b over h times y plus b. And now I'm integrating with respect to y instead of with respect to x. What about the limits? So I'm adding this up, every one of these rectangles, right? Going this way. So the key thing on the limits, guys, whatever the differential here is, this is dy, so my limits go in the y direction, starting down here at 0, going up here to y equals h. So this is 0 to h. So just to recap from last time, we found y bar last time with vertical rectangles, okay? And the limits on that were 0 to b. We were integrating with respect to x, even though we were calculating the same thing, y bar. Okay, so it's not because we're calculating y bar that this is 0 to h. It's because we're integrating with respect to y. That's what happens if I use the horizontal rectangles. So if you take a look at this, the math for what I have up there right now looks exactly the same as the math for when we used vertical and calculated x bar. Okay, except we're switching x and y. But let's just go ahead and bang through to make sure we believe the answer. Okay, it's going to be 2 over bh, right? And if we simplify this thing, I've got the integral from 0 to h. Multiply through, you'll get minus b over h y squared plus b times y dy. So if I work the integral, y bar is 2 over b times h. And how about that first term? Minus b over h y squared. Minus b over h, what do I do with that? Stays out front, right? Minus b over h. How about y squared? What's the integral of y squared? Y cubed divided by 3, right? And then I've got plus b. I've got to integrate y now, and I get what?
1 half y squared.
Yeah, y squared divided by 2. And then I have to evaluate the limits, in this case, 0 to h. Okay, and so we can see if the algebra works out. 2 divided by b times h. I put in the top limit here. I'll get minus b over h times h cubed over 3. Plus I'll get b times h squared over 2. That's the top limit. What happens when I put the bottom limit in? Yeah, I get 0 in both terms. Again, I encourage you to be anal about it and write it out, even if it's 0. Okay, do not get in the habit of forgetting one of the limits just because it's 0. For a polynomial, I get 0, right? An exponential, a cosine function, I do not get 0. Okay. All right, so let's look at the math here. What do I have? Y bar, 2 over bh. So I'm going to cancel h over here. I'm going to get minus bh squared over 3. And then over here I got plus bh squared over 2. What's bh squared over 2 minus bh squared over 3? It's 1/6, right? 2 over bh times bh squared over 6. Okay, and now take a look. What happens to the b? Cancels. 1 of the h cancels. 2 goes into 6 how many times? 3 times. And so the answer is h divided by 3, right? Which we knew it had to be. We did it last time with vertical rectangles. Okay, so the point here, guys, is that you can use any kind of elements you want to use to do an integral, right? This is a centroid problem. You know, you might be in, a different class taking a slice of something else that you're adding up. Okay? You get to decide what is the slice. When you write the slice out, identify what each one of your terms are that you need, and then after that, you just go from there. Okay? So I would argue in general, probably easier to use these horizontal rectangles to get the y bar and the vertical rectangles to get the x bar. Right? Remember when we did vertical rectangles to get y bar, we had like a 1/2 y quantity squared. It's messier algebra. So you can choose the slice in order to simplify the problem. Okay. Questions on that? All right, here's a punchline for you. Okay. All of this argument, right, about what a centroid is, it kind of lends, the possibility of another interpretation. Okay, and this is exactly the interpretation that ends up being used later on in mechanics classes like statics, like strength of materials, okay, like biomechanics. Okay, and so I'm going to say this is really like a final note on centroids. Okay, what if I put the coordinate axes at the centroids? Okay, so suppose the coordinate system, okay, is located at the centroid. Okay, so I'll draw a picture of what I mean here. Okay, so for example, in my triangle, right, let's say here's my triangular region, and I already know the answer for the centroid. It's 1/3 of the way, right? So I go about 1/3 of the way up, and I go about 1/3 of the way over. I apply the Klingbeil theorem on the dot, okay, and there's the centroid, right? And I put the axes right there now, okay? So this is y, and this is x, like that, okay, and this is G right there, okay, then by definition, okay, think about this, x bar, right, is the integral of x dA divided by the area. In this coordinate system, what's x bar equal to? Yeah, it's 0 by definition, right? The origin is at the centroid. Okay, and I could do the same thing. Y bar is the integral of y dA divided by A. Okay, and that equals 0. Okay, and so, you know, the bottom line is, if this is true, okay, then what's the statement? The denominator there, the area, that's a number, right? That's not infinity. Okay, and so if that quantity is 0, then that means the integral right there has to be 0. Okay, so another way to think about what a centroid is, which is pretty much physical, okay, is that, you know, this means that the centroid, another definition of it, would be essentially the location of the origin. Right? It's the location of the xy origin, okay, such that, right, the integral of x dA and the integral of y dA are both equal to 0. Okay, that's the statement. So, you know, what does that actually mean? Right? If I know where a centroid is, you know, now for any kind of shape, say, you know, like right here, okay, and so here's the xy system, x and y. Okay, if you want to think about, you know, the integral of x dA being equal to 0, then the idea would be I could slice this thing into rectangles, right, and I could figure out where is this thing balanced, right? The integral of x dA equals 0. Okay, this is what's called the first moment. This is the first moment of area, okay, about the y-axis. Okay, and so think about it. We talked about what does a centroid really mean, right? And we said, what if I could pull the shape off the board and balance it on the tip of my finger, right? Well, this piece is weighing it down on the right side. I got some pieces over here weighing it down on the left side. The first moment, you know, by definition, it's this area multiplied by how far away? X, right? So it is a moment. It's like a force times a distance. It's an area times a distance. Okay? And I can think about the same thing, the exact same shape, if I want to think about it in now the y direction. Okay, then, you know, in that case, maybe easier to visualize with horizontal rectangles. Okay, and it's the same argument. If I come in and I think about the first moment of any one of these rectangles, now about the x-axis, the integral y dA is equal to 0. Okay, and, you know, that is the first moment, okay, about, in this case, the x-axis instead of the y-axis. Okay. Questions? Centroids. All right, so this is, I got a geometric shape. I want to know where the middle is. The middle is where can I find a spot where things are balanced. Balanced in the y, balanced in the x, about the spot. Okay, a place where that's used a lot, besides, say, rigid body mechanics, right? In a rigid body, I got to know where the middle is, because I add up the forces to get 0. I add up the moments to get 0. If it's statics, if it's dynamics, I'm worried about acceleration of the center of gravity. I got to know where it is. In distributed loads, okay, the idea of centroids ends up popping up again. Okay, as does the idea of area under curves. Okay, so what I would like to do is go directly from the shape idea to how can I think about distributed loads acting on beams, acting on surfaces, and how does this idea of centroids and centers of mass matter for that? Okay, because this really this is the punchline of why you need centroids, centers of mass, integrals in statics. Okay, so distributed loads. Okay, and the example I'm going to look at here is hydrostatic pressure. Okay, and so what do I mean by hydrostatic pressure? Okay, easy way to think about this would be, say, what if I have a retaining wall that's trying to hold back, you know, liquid, the ocean, whatever you want to call it, okay, over here. So here's my wall, okay, and out here, you know, I've got fluid. Okay, so this is a fluid right here. Okay, and it's got a certain density. Let's say the density is rho. Okay, so Greek letter rho, we use that a lot for density. Okay, then you guys might remember, maybe from some high school chemistry, high school physics, okay, if I have fluid that has a certain density, okay, as I go down underneath the fluid down here, okay, so now this is the ground down here. Okay, then I start to build up pressure, right, as I go down. Okay, and essentially what pressure is as you start to dive down, it's essentially the weight of all the fluid on top of you. Okay, but pressure acts in all directions, right? So I could be just, you know, doggy paddling down here at the bottom, and the amount of force on me would act on every part of my exposed body, the bottom of my feet, the top of my head, whatever, right? It's a normal force that acts on that, pressure. Does anybody recall, okay, and I'll ask a leading question, right? Gravity, G, goes down, okay, and, you know, maybe the entire height of this thing, okay, is H. Anybody recall a formula with some of these parameters that are up on the board here for what's the value of the pressure all the way down here at the bottom of the depth here? I got density rho, I got gravity G, I got height H. High school physics, maybe chemistry, you would have looked at some of this. Anybody?
PGY or PGH or something?
So it's not P, Greek letter rho. Rho GH, okay? Rho GH is the value down at the bottom. Okay, so now what I want you to think about is, so the pressure is rho GH at the bottom. What's the pressure all the way up here at the top? 0. So the pressure changes as you go, right? As you go down, it gets deeper. And if the value at the bottom is rho GH, then what do you think the value is at any depth y, right? So if I take a coordinate system at the top here, y, where y goes from 0 over here to h, at some value y, what do you think the value is? It'd be rho g times y, right? When y is h, it'd be rho gh. So what happens is you get a linearly varying pressure, right, that acts, the deeper I go, the more pressure I have acting on the wall, like this, okay, all the way down to the bottom, like that, okay? So that's the idea, right? And so what this is this is the pressure distribution, pressure as a function of y. Okay, and so the pressure is equal to, have to be really careful with your letters here. Don't confuse your P and your rho. Pressure, P, as a function of y, is rho G times y. That's the equation. Okay, so this is a P for pressure. Rho is density. Okay, so P of y, this is pressure. Okay, as a function of y. By the way, what are the units on pressure? Pascal is 1, but give me, I mean, what's a Pascal if you don't know what that is? Okay, so that's a conversion factor from pascals to, right, to atmospheres. Can somebody tell me, like, physically what is pressure? Pounds per... Okay, so in English units, it's pounds per square inch. Newton per square meter, that's a Pascal, right? So the idea is it's force per unit area, right? So I'll write this as, this is either Newton per square meter, it could be pound per square inch. By the way, pound per square inch is also known as what? PSI, right? It's like the pressure in the tire of your car, okay? PSI. All right, so I got force per unit area, okay? What I would like to know, okay, is what's the total force that's acting on the wall? Okay, this is the question. So, what is, okay, the total force acting on the wall? That's the question. Okay, so the issue with this is that the force is not going to be the same, right? At the very top of the wall, do you think I have a lot of force? No, I've got no pressure right at the top, right? At the very bottom of the wall, right, and in fact I know what this length is right here in terms of pressure. This is rho GH right here, right? That's the value right here of the pressure as I get down. Okay. So how do I go from pressure to force?
Or just one integral?
Integrals. I mean, so back up the cart for a minute before we get to an integral. Okay, there'll be an integral in here somewhere. In general, if I have pressure, force per unit area, how do I get from that physical quantity to a force? I got to multiply by an area. Okay, now the problem is the force is not the same at all depths here. Okay, so little hint, in engineering, whenever you're trying to figure something out and you have something that varies continuously, probably ought to break it into slices and see if you can understand it at one point. Right? And so let's think about it. Let's say I'm down here at a certain depth. This is the wall right here. Okay? And I probably need some dimensions on the wall. Let's say in addition to the height, I'll use the width of the wall. We'll call it B. Okay? Then if that's true right here, okay, then if the width of the wall is B, okay, then this area over here would be what? So B is the length of the rectangle. What would be the height of the rectangle? Here's the height of it. Let me ask you this. What is the variable here? Is h a variable or is that a parameter? Yeah. So, right, this is dy right here, okay, is the thickness. So the dA apparently is the width times the infinitesimal height, which is dy. Okay, so I got b times dy. Great. So then, how would I calculate the force that acts, say, right here? Okay, I'll put that in there like that, and I'll call that the force. Let's call that dF. I got pressure that varies as I move all the way down here, right? And it acts on the wall. So the force dF that acts just on this piece right here, right? Wouldn't I get that by taking the pressure at this value and multiplying by this area? Okay, so at any point, okay, what I have is part of the force. I have dF, right? And that part of the force is the pressure. This is not the rho here. It's the pressure as a function of y, okay, times dA. Okay, and so I can put in, you know, what this is going to be. The pressure as a function of y. I've got the equation. It's rho gy. So this one's a p. I'm replacing that with rho gy. And the dA we've identified here as b times dy. So if that is one little piece of the force at one point along the pressure distribution, how would I get the total force? I got to add them up, right? Now how many DFs do I have? I got an infinite number. So when I got to add up an infinite number of things that act over an infinitesimal slice, right? Am I not evaluating the integral, the sum of all the DFs? Okay, and so the idea is that integral is the integral of this. It's rho g. I'm going to move the algebra here, put the b next to it. Rho gb times y dy. So I'm integrating with respect to what variable here? Y. Okay, and so if that's true, then my limits on this should be what? Yeah, so I'm starting here, and I got DFs at every single point, and I'm adding up all the DFs the entire way down until I get to the bottom, which is h. So now we're getting somewhere. Okay? So that's the total, right? And again, this is the total force. I'm going to call it F, right? It's the integral dF. So this is the answer for what the force is. F is going to be the integral from 0 to h of this guy, rho gb times y dy. Is that a hard integral to evaluate? Not really. What do I do with the rho gb? That's a constant. Rho is the density of the liquid. It could be water, could be molasses, could be caulk, okay, whatever it is. Rho. G is gravity. B is how wide the wall is. Those are all parameters. I got to do an integral now. Integral 0 to h of y times dy. Complicated integral? Pretty trivial, right? So, help me out. F is, I got rho gb out front. Integrating y now with respect to y. Yeah, it's y squared divided by 2, right? Just like this could be integrating t dt. It could be the integral of x dx. This is the integral of y dy. Okay, it doesn't matter what the letter is. I do the integral. I get y squared divided by 2, and I got to do the limits from 0 to h. So when I put those in, I get f is equal to, right, rho gb, and I'm going to get inside here h squared over 2 minus bottom limit is going to give me 0. So apparently the total force, right, is, this is the answer, F is going to be equal to 1/2, right, rho gb h squared. I'm going to write it like this, 1/2 b times rho g h squared. Okay, like that. So that's the total force. All right, so here's something I want you to think about. Take a look at what my force distribution looked like here. I'm just going to draw the force by itself. Okay, what shape is that? It's a triangle. The base of it is already labeled over there, right? The base of it is what? Rho gh. The height of it, h. Right? So, what's the area of that triangle? So, F, right, over here, 1/2 rho gh times h, 1/2 rho gh times h, right? This is 1/2 the base times the height. Right? The only difference is I've got a per unit width, so I've got a b out in front. B. Okay, and so the point is this part of it, if you forget the b, which is the width, okay, looking at the picture, that is the area, right, underneath the curve. Right? And so the point is, that area, by definition, right, F is equal to, this is the B, it's the integral of the load, P of y dy, right? And then I'm multiplying the whole thing by B. And so the conclusion is, if I want to find the total force for a distributed load, and I've got a curve that represents the distributed load, then the total force is what? Yeah, that's it, right? So the point is the total force, all right, I've got it written right here again. Okay, this is it. If the B comes out, F is equal to B, the integral from 0 to h of rho g y dy. This is the area under the load, right, P of y. Okay, so if this was load per unit width, which is what it would be if I multiply by width, okay, then if I have a distributed load that's given to me as load per unit width, then all I need is the area of the load curve, and that gives me the total force. Okay, and so the statement is total force is the area under the load. Okay, and this is a result that we use over and over again in statics all the time. Okay, need the area under the load. Questions about that? All right, let me ask you this question. We'll move on maybe to a better example of it, but if I'm thinking about this wall being able to retain this fluid, okay, is the total force the only thing that matters, do you think?
The maximum force.
The maximum force, well, that's actually true, right? The maximum pressure, I could get a local problem in the material down here. That's a good point. What about the overall equilibrium of this wall? Like, I don't want the wall, you know, to actually, if you guys remember Hurricane Katrina a number of years back, right? When they had the levees that failed, hey, what actually happened when the levees failed is, you know, levee is just a piece of land, right, that's designed to hold back floodwaters. Okay, that was a case where it was really just a problem with the total force. The force was too big. The levees didn't topple. They got translated. Okay, they just moved. And so it just plain pushed the barriers, and that's it, came in and flooded. Besides this thing translating, what else might it do?
Well, I know it was Hurricane Katrina, but where?
What, that was the one down in New Orleans, right? So,
How's that place doing?
I think they're recovered now. Doing all right, okay? Yes, question? All right, so the face of it could deform some, that's true. Okay, think about this wall more as a rigid body. Okay, besides translating, what else could it do? Just think about the motion of the body. Okay, maybe this is a better example. This is a ceramic cup, so I'm going to have to be careful, right? If I want to translate, it's full of coffee. If I want to translate this thing along the table, I can do this, right? Right? What if I push it all the way up here at the top? Ugh, I might have a problem, right? So translation's one thing, rotation's another thing, right? And so I guess what I would say is the same force is not all created equal, right? When you're thinking about a rigid body equilibrium. In other words, you know, where does this total force, the area under the curve, where does that act? Right? I mean, do you think does it act up here? Does it act all the way down here at the bottom? No, it's distributed, right? So when I think about this thing being in equilibrium, it's not enough to just say, well, it's got a certain total force. I've got to understand really where the resultant of that load is properly applied to the body. Okay, and so this brings us to the next topic, okay, similar to this. And it's the idea of distributed loads on your favorite topic, beams. Okay. So, distributed loads on beams. Another topic from statics and also mechanics of materials. Okay, and here's the idea. What I would like to be able to do is take a load on a beam, okay, that could be any kind of load. So I'll draw it here with what we call the simple supports, which is like hinges at the end, okay, like this. And let's say that I've got any kind of function for a distributed load here. Okay, so it's a load that is not uniform, right? And this is the y direction, this is the x direction, so the origin is over here at the left end. Okay, and I've got a certain load w of x, just like we talked about in the derivative problems on a beam. And this guy is a force per unit length. Okay, so keep in mind over here, right? Force per unit length would be what this is if I divide both sides by b, right? Then I'd have f over b, and I've got this integral. So it's the reason why distributed load problems, in real life, I can't apply a force per unit length to anything. I can apply a pressure to a surface, and if I multiply by the width, then that gives me force per unit length. Okay, so that's how you have that. So if you think about some weights that are stacked along this beam, or the weight of the beam itself, force per unit length. What I would like to do is replace this with what we call a statically equivalent load. All right, and so based upon what we just talked about, okay, what do you think would make a load equivalent, right? If I could take this entire distributed load and for the purpose of equilibrium on this entire beam. Okay. For the purpose of equilibrium, I'd like to replace this entire load with one force. Okay. Now, take a look at the picture. If I'm going to replace it with one force, first of all, what do you think that force has to equal? Say again? The total force. All right, and if this is w as a function of x, how would I get the total force? By taking the area, right? This statement right here, the total force is the area. So I better have the same total force. That would be equivalent. But take a look at the way I drew this one. Do you think that total force should be placed here? No. All the way at the left end? No. Somewhere in the fat spot, right? So we'll guess what that is. I'm going to say here. Okay, not in the middle, somewhere in the fat spot. And so I don't know where that location is. This is y at x. Okay, I'm going to use a small l to denote the location of the force. Okay, and I'm going to call the force r, which is the resultant. And as was just suggested, the way I'm going to get r is I'm going to have to get the area under the curve, which is the integral of w of x dx. Okay, and of course, this beam's got some length to it. I'll call the length capital L, like that. Okay, and so I will have to integrate from 0 to capital L w of x times dx. Okay, in other words, this is the area under the load, w of x. Okay, and so what we would like to be able to find out here is already demonstrated that to get the same total load r, I need the area under the curve. But I'd like to demonstrate where I should put the r, okay, in order for these two problems to be statically equivalent. By the way, statically equivalent means that the statics is the same. Okay, and what the statics is essentially what are the forces that have to be at these pins in order to keep this whole beam in equilibrium. So just to be crystal clear, since you guys are doing beam deflection problems, you got them on the exam coming up, do you think this beam deforms the same way as this beam? Right, I mean, a piece of material over here has no load on it, right? piece of material here, the real beam, it has load on it. All right, so locally, the deformation of the beam is not the same. That's why we call this statically equivalent. What is the same, if it's the total load, and I put it in the right spot, what is the same is what's going on the external forces, what's going on at the pins, okay, to keep this at equilibrium. Okay, so for the purpose of statics, this would be equivalent, not for the purpose of deformation. All right, so here's the idea. To have this thing be equivalent, in addition to the force, right? Think back to the Starbucks cup here. In addition to having the same force, which might tend to translate, right? If it wasn't fixed by the pins, it would move it down with the same tendency. I'm also worried about whether or not I'm going to tip it, right? So in addition to the force, I'm worried about balancing the moments, okay? And the moments, again, high school physics, they would call that torque, force times distance. Okay, so here's the idea. Okay, in order to be equivalent, okay, the resultant must have the same moment. Okay, as the distributed load. So the question is, how do we calculate a moment? So, case number one, let's look at the distributed load. You know, what would be a moment on a distributed load? Well, we'll draw it over here again, okay, and see what that might look like. So here's any kind of shape for the load right here. Okay, and here's y, and here's x. Okay, and I would like to take moments, okay, about x equals 0, for example. So what a moment is, okay, is a moment is a force multiplied by a distance. Okay. So here's the idea. This is any load W of x. Okay. Let's take a piece of that load right here, okay, and let's calculate the force over some infinitesimal distance here. Okay, and you know, if this little strip is dx, right, then this piece of force right here, I'm going to call that dw, and that's going to be w of x times dx. Right? So at any location here, I've got a value of the load. That's the w. Okay? The width of it is dx. So if w is force per unit length, if I multiply by the length, I get a force. This little piece of load can be located any distance x from the left side, right? So every one of these pieces of the load, if I undid the support on the right, every one of these pieces would make these things want to spin, right, this way, clockwise. If this was a hinge and I put this load here and I didn't have a support, this thing would go down, right? So every one of these is making it spin. The one all the way here doesn't make it spin, but the further I get away, I get a bigger moment arm. Okay, and so force times distance is what makes it want to spin. Okay, and so how do I calculate the moment for this guy about the origin? We'll call it MO, the O for the origin. I need to take each one of these forces, okay, and I got to multiply it by the distance. And then I got to add them up. So I'm going to add up the integral of x dw, right, or the moment about the origin is the integral, dw is w of x dx. So it's x times w of x dx, and I got to do that over the whole length of the beam. All right? The beam starts here at 0, and it ends at x equals L. So I got to go from here to here, 0 to L. So that's what the moment would be. I'm going to call this equation 1 for the distributed load. Okay, and so the question is, what would be the moment for the equivalent load? Okay, and so we'll call this case number 2. Equivalent load. Okay, and what would this guy look like? Well, relatively straightforward. If this is an equivalent load, okay, and again, here's the origin, y and x. We already said that this resultant r, which is the area under the curve, the integral w of x dx from 0 to capital L, is located some distance small l from the origin. So if the moment is the force times the distance, help me out here, what would be the moment of the load r? So I got the total force r, and the moment is, I take the force times the distance, right? That's what makes it spin. What's the distance? L. So this one, pretty trivial the way I drew it, right? Isn't it just r multiplied by L? Right? This force times that distance has to be the same as the sum of all of these forces times all of their distances, right? Each one of these forces acts over an infinitesimal width. I got to add up the total to get the total moment. So I need r times L, but the r is actually an integral, right? And so it's the integral from 0 to capital L, w of x dx. That's the r. That whole thing is multiplied by L. Cleaner to just write the L on the left side. All right, so I'll write this as m naught, the moment, is small l times the integral from 0 to big L of w of x dx. So that guy, I'm going to call equation 2. So to recap here, I got two loads. One's distributed, one is supposed to be equivalent. I already know that the equivalent one has the same total force, because I took the area under this curve and said, let's use that for the r. So the total force is the same. Question now is it in the right spot? If it's in the right spot, then the moment has to be the same. For the distributed load, this is the moment, equation 1. For the point load, this is the moment, equation 2. So if it's equivalent, then what can I say about equations 1 and 2? They got to be equal, right? Okay. So this is the key for equivalent loading. Okay, I need to set the two equations equal. Set 1 equal to 2. So what's the conclusion here? M naught, this is equation 1. It's the integral 0 to capital L of x, w of x dx. And that's supposed to be equal to equation 2, which is small l times the integral from 0 to L of w of x dx. What am I trying to find here? Am I trying to find r? I know r, right? R is the area under the curve. I'm trying to find the place where I put the r, which is what? Small l. So don't I want to solve this for small l? All right, this is the location where I want to put the load. Take a look what you get. Solve for small l. The numerator is the integral 0 to big L of x, w of x dx. The denominator is the integral 0 to big L of w of x dx. This is where I put it. And next to this, I'm going to write a little note for you guys. Do you remember this equation? X bar, the integral 0 to L, right, of what? What's the definition of the centroid? We had x, right, y of x dx, divided by the integral, y of x dx. Yes?
Can we have something else?
Oh, sorry. Yeah, so we'll have to take a facilities management break. Okay, so the point is, I'll call somebody in a minute, is that the value of L, take a look at the two equations, right? This is the centroid. Okay, so you put the load at the centroid. Give me a second. All right, guys, I'll tell you what we're going to do is we are done with centroids, everything that you guys need for the homework. All right, so let's call it a day. Cover yourselves, don't get sick, exam tomorrow night. We will pick up with dynamics next time, okay? You are good for the homework due this week.